Today we are going to discuss radioactivity and in particular details of gamma decay and then complete picture of elementary particles related to the nuclear physics. I am Dr. Nasir Majid Mirza and I will be discussing this in today's lecture. If we look at the gamma decay, there are certain properties that have been seen. They are electromagnetic radiations, they are photons, they are like X-rays, have a very short wavelength. Their range is of the order of 10 to the power minus 10 meters to 10 to the power minus 13 meters. They affect photographic plate. They are unaffected by the electric and magnetic fields. So they do not have any charge and no Lorentz force is experienced. Their ionization power is low, about 1/100th of beta particles. So do not cause ionization directly. Their velocity is same as that of the light. Their penetration power is very high, about 100 times more than that of beta particles. Their interactions are different, so they penetrate deep. They can only be stopped by the hard materials like lead, and thick sheet of lead will stop gamma rays. It is generally the shielding material for gamma rays. When gamma decay occurs, no particle really is ejected in the particle sense from the nucleus. I mean to say, having a real mass or spin, no such particle is emitted. This decay is really associated with high energy form of electromagnetic radiations. A gamma ray photon is released. Gamma rays are photons and they have very high energies of the order of a million electron volts. So they do not change the structure or the composition of atom, instead only change the energy of the excited atom. They bring excited atom to lower excited state or to the ground state. Experiments have shown that the protons and the neutrons that are located at the discrete energy levels within the nucleus experience this cascade reaction, that they fall from high energy level to low energy level, and in doing so, they really emit photons. The nucleus makes the transition from high energy level to low energy level, and gamma ray photons are emitted and their energy is high. In general, the equation that represents such a process is, we've shown with X, the parent element that is excited with the star having A number and Z number, and then it decays to a less excited state or a ground state with X, A, and Z plus a gamma ray is emitted. The gamma emission is usually followed by beta decay, and the selection rule may not allow the direct transition to the ground state of the daughter nucleus. So remember that for gamma decay, the mean life is very short, of the order of 10 to the power minus 11 seconds. And we expect that gamma rays will impart certain momentum to the nucleus, and when they are really moving, they have momentum. If the energy is given by h into the frequency, some texts use nu. Here I have shown here F, H into F is the energy, and the momentum is F divided by C. And this is the momentum carried by the photon which is coming out of the nucleus, and there is a recoil, mc square divided and the p momentum. So we can have the momentum of the daughter nucleus and the momentum of the gamma ray. Knowing that the atom does undergo the gamma radiation, it is important to determine the frequency released in the gamma radiation. If the initial and the final state of the nucleus is known, then taking the difference of the energy will give us H into nu or H into F. And here the initial and the final state of the energy of the nucleus is EI and EF. The frequency is nu, and it is the frequency of the emitted photon. I have shown here the isotope cobalt-60, and it is with the beta decay, and 99.88% is the probability of this beta decay, and about 0.12% is this beta decay. If it decays to this most of the time, then it will fall from this excited state to the another excited state, and will release this photon, this energy, 1.1732 million electron volt. This is a signature of cobalt. And then it will not stay here, it will fall again to the ground state and will emit 1.13325 million electron volt. So 1173 and 1332 keV are the two gamma rays energies that are released when the cobalt undergoes a beta and followed by the gamma rays. The gamma decay is basically due to the electromagnetic interactions, and it is treated as a perturbation. Emission of the gamma ray is really caused by the interactions of the nucleus with the external electromagnetic field, and it causes them to become stable, more stable, and excited level of isotope is brought to the ground state by emission of these. Besides, gamma electromagnetic perturbations can also be introduced in the nuclear decay through internal conversion, where one of the atomic electron is ejected, and since the nuclear wave function has a definite angular momentum, the external electromagnetic field has to be decomposed. So we can see here one excited nucleus going to ground state by emission of the photon, and we see the reaction. Nothing changes with the nucleus except this, that the excited level goes to the ground level. Let us look at the kinematics. Here I have shown few things that are really related to the photon emission. You can see here that the initial energy and the final energy and the gamma ray energy and the recoil term for the nucleus. So this is the distribution. So the difference between initial and the final energy appears as a gamma ray energy and a very small recoil energy. For A is equal to 100 and E gamma equal to 1 MeV, the recoil energy is about 5 electron volts, which is very, very small, so we can ignore this. And the natural line width of the radiation is even smaller than we show here. So we really don't see that. Here I have shown here that m naught c square is the state excited level, and it is beta plus emission or the electron conversion, which goes in this direction, and the gamma emission is in this direction, where Z remains unchanged, and the beta minus is emission, which is going to change the Z number by 1 plus. The emission of photons without recoil is possible if one implants the nucleus in the lattice. Such a case is seen when the recoil is taken by the whole lattice and not by the single nucleus. So the quantum mechanical treatment of such an energy emitted by the gamma radiation takes away the total energy difference, as we can see here in the equation. One competing process with the gamma ray decay is the internal energy conversion effect. An atomic electron is ejected instead of a gamma ray, and the electron, especially those which are within the inner orbits, they come out and they spend a large fraction of time in the vicinity of the nucleus. So the source of electromagnetic field, the electron kinetic energy is given by that. The virtual photon exchange can also occur, and the process can be between L is equal to 0 states. Here we show one electron spectrum in which the internal conversion and the beta decay in the background both are shown together. And you can see here that the internal conversion process has sharp peaks. So the spectrum is a discrete spectrum for the internal conversion, and it is a continuous spectrum for the beta decay. And for a material which has a competing internal conversion and the beta decay, we see the internal conversion as a sharp line as opposed to a continuous spectrum. So such internal conversion processes become very important when the nucleus is heavy and the large Z values are there, because such processes are proportional. Their cross-section, the reaction cross-section is proportional to ZQ. The larger the value of Z, the larger will be the competing internal conversion. Internal pair production is also another competing thing in which the electron and positron pair is emitted in place of a gamma ray. This can happen only if the gamma ray energy is very large as compared to 2m naught c square, or mass of the electron c square, which is 1.022 million electron volts. So if you look at such a happening, in that case, the gamma emission is broken. That gamma ray is broken into two decay lines. One is the electron and the other is positron. Or this kind of a decay also is possible, in which the scattering occurs. Here we show that the electron scattering is like this, in which the conservation happens, the recoil of the nucleus takes place. In this case, the recoil do take place, but the two pair, when the gamma ray is converted, the two electron and the positron creation is such that they are really with a smaller angle as compared to the large angles shown here. Here we show the ZR90 and its a decay scheme, and we show here the internal conversion process also. Usually this process is a several order of magnitude less as compared to the allowed gamma ray decay. The pair production rate is large when the internal conversion rate is very small. That is the region of the low atomic numbers and the high transition energy. So remember, when Z is low, then if the energy of the gamma ray is very large as compared to 1.022 million electron volts, then such a gamma ray can get converted into internal pair production. Let us see fundamental particles that are really developed over the years and understood. Here I show in a purple color the quarks. The quarks are up, down, charm, strange, top, and bottom. These quarks have other properties as well. Let us see the other properties. The mass in terms of million electron volts per c square is written here, and let me go through this one by one. The mass of the up quark is 2.3 million electron volts per c square. It is about 1.27 or 1.3 million giga electron volt per c square for charm. It is of the order of 173 giga electron volts per c square for top. It is of the order of 4.8 million electron volts for a down quark. Up and down are of the order of million. The strange and bottom has also of the order of million, but strange has up to 95 million electron volts per c square, and the bottom has 4 GeV per c square. Their charges are: up has a charge of 2/3. The down has a charge of 1/3 minus. Similarly, charm has 2/3, top has 2/3, the strange has 1/3, the bottom has 1/3. Now, if you see that up, charm, and top, all of them are 3/2 charge of electron, and down, strange, and bottom have 1/3 electron charge. All of these 6 have spin half, so they are fermions. Now we go further to these green category. The green is leptons. And leptons are basically the electron, muon, tau, the electron neutrino, the muon neutrino, and tau neutrino. Let us see the properties. Their energies are, the masses are, equivalent masses are given. The tau masses are large. The muon and the electron masses are small. The neutrinos have very, very small masses. And all these are spin half particles. Their charge is -1 or 0. The muon, the tau, the electron, the -1 charge of electron, and the spin half particles. Now we come to these gauge bosons. These are basically the gluon, the photons, the Z boson, and W boson. The gluon, 0 mass, 0 charge, integral spin 1. Photons, 0 charge, 0 mass, 0 the spin 1. Z boson has a mass in about 91 GeVs per c square. Z has 0 charge. Z is spin 1. Similarly, W has spin 1. It has charge plus minus 1. Two types of bosons, the W bosons, the plus W plus or W minus, and their mass equivalent is 80.4 G. If we look further, all these orange colored gauge bosons have the spin, integral spin, and therefore they obey the Bose-Einstein statistics. So they are bosons. The Higgs bosons are different and have been placed in a different category. Their energy equivalence is very large. It is 126 GeV, 126 GeV. They have no charge, and their spin is 0. We will talk more about that in coming. Remember that the fundamental particles create the other things like hardons, these mesons, the neutral pions, the up and its antiparticle, the baryons, the protons, up and down. So all mesons and baryons we find can be constructed with 6 quarks and their antiquarks in a standard model. There is a standard model in high energy physics, and we will not discuss that in detail here. But remember that this model has the nomenclature and justifications. No single quark has ever been seen, have been detected in isolation. Only union in 3 quarks or the quarks and antiquark pairs have been discovered. So, in brief, the basic particles have this general trend. All visible matter in the universe is made from the first generation of matter particles, that is up quarks, down quarks, and electrons. The second and the third generation particles are unstable and quickly decay into stable first generation particles. So we do have generations of all matters. Why there are 3 of them, we don't know at the moment. We cannot really rule out the possibility that there will be more quarks and leptons as we progress further in experiments, because we have not yet discovered, but we cannot rule it out. We don't have theoretical basis. Perhaps quarks and leptons are not fundamental, but they are made up of even more elementary particles whose composition we observe as a quark. But at this stage, we don't know how to further break quarks. I show you the picture again, and with the representation that the quarks, 6 quarks, the up charm, the top, the down, the strange, and the bottom, and the leptons, and all the bosons, all the types of bosons that are really making the structure, the matter. So these particles and their antiparticles are really all that are needed to create stable particles in the universe. So if I turn to this chart, I see that the construction is simple. Generation 1 is the electron, the neutrino, the quarks that are up and down quarks. The leptons have spin half. The Then there are muons and neutrino in second generation, and they have their counterparts in the quarks, strange and charm quarks. Similarly, the third generation, the tau and the tau neutrino, and they have the quarks bottom and top quarks. So their rest energy progresses as we move further towards the third generation. We have not been able to go further because the very high energies are needed to spell out and see any other generation which is there. We stop here after covering all the families as this, that hardons are made up of quarks, baryons, the heavy particles made up of 3 quarks, mesons are the medium particles that are made of quarks and antiquarks, and leptons are the light particles, that is electrons and neutrons. So if we see the beta decay, if we see the beta decay, we come to know that in beta decay, in beta decay, we see that the proton getting converted into neutron or a neutron getting converted into a proton is basically the exchange or that is taking place in the up and down quarks. And the mediating particles are the bosons. So what we say is simply is that the bosons are really the carriers, the force carriers that are really there, and they are responsible for the interactions. For the electromagnetic interactions, the force carriers are photons. The weak interactions, Z particles and the W plus and the W minus are responsible. And for the strong interactions, different colors and the combinations of the gluons are responsible. And for gravity, probably a graviton is responsible. And we now know that the rest energy and their charges are known to us, and we have the methods to explain the things that are happening around us. Everyday interactions, including all the chemistry, can be handled through the electromagnetic interactions, and the weak interactions will let us know the beta decay and other particle transmutations and transformations, and the strong interactions will let us know what holds nucleus and how the mesons are together and how the nucleons are together, and the gravity is really thought to be responsible to assemble the large masses, and yet we don't know the other possible particles that are responsible for the gravity. We stop here with a general notion that fundamental particles and the fundamental forces have been defined, and we can move further with the study of the decays and the decay processes in next lecture. Thank you so much.